Hello everyone, I'm Xin from Beihang University. Here I introduce VClinic, a portable and efficient framework for fine-grained value providers. This is the outline of my talk, which contains 5 parts as shown in the slide. First, I will introduce our background and related works. Production software is becoming more complex due to its deep software abstractions, as well as sophisticated control and data flows. Such software complexity usually leads to unexpected inefficiencies that are hard to detect and locate by manual inspection, whereas coarse-grained value performance profiling tools such as both ASPLOS'23 and VClinic can identify the software inefficiencies by utilizing PMU. However, recent researchers have already proved that value-related efficiencies such as dead right, redundant load, and redundant zero cannot be effectively identified by such tools. In contrast, fine-grained value providers have revealed a promising way to detect value-related inefficiencies with accurate root cause analysis for optimization guidance. Among them, dynamic binary instrumentations can provide the most accurate profiling results, which is one of the most widely adopted techniques to develop fine-grained value providers. Fine-grained value providers mainly rely on compiler passes and binary writers to instrument the codes for analyzing runtime values. However, compiler-based approaches either need source code or limited to specific domains for value profiling. Generally, the existing fine-grained value providers rely on specific implementation techniques for each target platforms, which is difficult to achieve portability and efficiency for fine-grained value providers at the same time. The existing abstraction for tool developments includes performance instrumentation library, compiler-level DSLs, and binary instrumentation frameworks. However, they need to develop instrumentation at the function or instruction level. The developer is also error-prone and hard to achieve efficiency or portability at the same time. In contrast, VClinic is the first portable and efficient framework with for brand-centric view to build the fine-grained value providers for fully optimized binaries on multiple platforms. Next, I will introduce VClinic designs. Although fine-grained value providers can detect value-related software inefficiencies with binary instrumentation, it is challenging and error-prone to implement efficiently across different platforms. Firstly, tightly coupled implementation of value collection and value analysis leads to conflicting goals for achieving portability and efficiency. Implementations with clinical insertion may have better portability with poor efficiency, while efficient inline assembly and instrumentation will lead to error-prone and poorly portable implementations. Therefore, we first decoupling the value tracing and value profiling to achieve portability and efficiency. Secondly, efficient architecture-specific instrumentation leads to heavy engineering and poor portability. Thus, value tracing should be architecture agnostic to hide the underlying implementation details for portability. Thirdly, the instruction-centric profiling forces developers to spend more effort on extracting values rather than analyzing them. Thus, we propose our operand-centric profiling to facilitate value extraction and attribute a collection with more intuitive view for value analysis. Based on Principle 1, 2, 3, we propose the operand-centric two-level designs, including vTracer and vProfile. vTracer has architecture-specific implementation details with trace buffer. vProfile provides operand-centric view for developers, which contains interfaces with operand filter, target operand attributes, and record actions to handle the collected value records. Next, I will introduce our methodology and implementations. Based on the two-level operand-centric designs, we implement VClinic, a portable and efficient framework to develop fine-grained value providers. VClinic is built atop DynamoReal and thus supports x86 and ARM platforms. Specifically, VClinic relies on 4 phases to implement the two-level operand-centric designs, including initialization, instrumentation, runtime execution, and finalization. The implementation overview of VClinic for instrumentation and runtime execution phases is shown in this figure. In initialization phase, the developer needs to notify VClinic what operand attribute to be collected and register the analysis callbacks as the user-specified snapshot action and record action. Besides, the developer can also register a user-specific operand filter to filter out unnecessary instrumentations for extracting and tracing operand attributes with reduced performance overhead. Afterward, VClinic allocates thread local traces for each data length and type when a new thread is launching. Such span-grain trace allocation can avoid instrumentations to trace LA and LE for higher efficiency. Note that when restricted order flag is set during initialization, VClinic will allocate a single thread local trace for all data types to ensure that tracing order and instrumentations to trace LA and LE are still needed. After initialization, the instrumentation phase in VClinic is triggered each time a native basic block is detected. As shown in Figure A, VClinic examines all instructions within the basic block to find all trackable operands. VClinic supports tracing the operand attributes before reading, before writing, and after writing the operand. For each valid operand at each trace point, VClinic applies static operand attribute detection by analyzing the instruction and operand to extract statically determined operand attributes. User-defined annotation is derived by triggering the user-defined annotation callback when registered within the initialization phase. After detection, the SOA is passed into a user-defined operand filter to filter out the expected operands for instrumentation. Only the operands that remain after operand filtering will be instrumentated with lightweight operand tracing and trace buffer management. After instrumentation, the instrumentated basic block will be executed with trace buffer management and vProfile/swap actions, as shown in Figure B. Specifically, when entering an instrumentated basic block, VClinic first detects whether the trace buffer will be overflowed according to the number of tracing elements residing within this basic block. VClinic triggers for /swap actions for handle the specific trace buffer that is detected as overflow. Specifically, the trace's head pointer and its length are passed into the /swap actions, including user-specified /swap action and vProfile /swap action. To enable operand-centric view defined in vProfile, VClinic extracts the value record organized as shown in slide from each compliant trace element and pass it to the user-specified record action for further analysis. As VClinic utilizes a uniform visual layout as shown in slide for value record with concise API design. The attributes not instrumentated will remain as undefined values. After handling the BTS, the trigger's trace buffer isn't clear. For each operand with value tracing instrumentations, the inserted lightweight operand tracing instructions extract the requested runtime operand attributes. The extracted operand attributes are then stored in the trace buffer using compact value tracing format, and the tracking pointer for the trace buffer is then forwarded for the next operand tracing. When the thread or program exists, the thread local trace buffers are triggered as VTS, and corresponding actions are also triggers to handle the non-empty trace buffers. All memory spaces allocated by VClinic are freed at the finalization phase. For instance, we introduce how to implement redundant value profiler with VClinic. Value redundancies are inefficiencies that write the same or similar values into the same memory locations, which indicates optimization of potentials for redundant computations. Specifically, value redundancies include register level and memory level redundancies, which need different detection policies for better efficiency. With VClinic, we can simplify the separation of these two levels by using two different operand masks as shown in the line 1 to 5, where mask 1 is the register level mask and mask 2 is the memory level mask. These two levels will then be separately handled within record action by examining the operand attributes in the trace record. For more details, please refer to our paper and API docs. Next, I will introduce our evaluation results. We evaluate VClinic on both x86 and ARM platforms with detailed hardware and software configurations listed in the table. To demonstrate the efficiency of VClinic, we implement representative value profilers detecting redundant load, redundant zero, dead stores, and value redundancies with VClinic. We also evaluate corresponding state-of-the-art x86 specific value profilers implemented for comparison. For evaluation, we choose representative benchmarks from NPV with Class C input size on both platforms. To demonstrate the productivity of VClinic, we count the overall LOC, the value LOC, and calculate the code efficiency for each evaluated VClinic and pin-based value profiler. As shown in the table, the overall line of cost to implement these representative value profilers within VClinic is significantly less than the implementations with PIN. Besides, the cost efficiency of all evaluated value providers implemented with VClinic are significantly higher than PIN. Note that the representative tools implemented with VClinic are naturally applicable to both x86 and ARM platforms, which is not supported by PIN-based implementations. To better demonstrate the performance and memory impact of VClinic, we implement 8 representative points as shown in the slide, and the evaluation result is shown in the table. We can see that the less target operands required, the lower TO and MO incurred by VClinic due to less binary implementation. Besides, for most programs, the strictly ordered VClinic incurs more TO than relaxed order VClinic. This is because the relaxed order VClinic leverages per data type trace buffers for value tracing and thus avoids interpretations for tracing detailed data type information. In sum, VClinic enables performance portability for both platforms with acceptable overhead. Representative value providers can be efficiently constructed with VClinic on both platforms with acceptable overhead. Guided by the value providers built upon VClinic, we can achieve significant speedup for real-world programs on both platforms. Finally, we conclude our work. In this paper, we present VClinic, a portable and efficient framework for fine-grained value providers based on operand-centric two-level designs. The design of VClinic can effectively hide the implementation details of runtime instrumentation and value tracing to help developers to concentrate on software efficiency analysis. The implementation of VClinic is highly optimized with methodologies such as static operand attribute detection, lightweight operand tracing, and trace buffer management, which leads to value providing portability and efficiency. Our evaluation results show that VClinic can ease the development of representative value providers with acceptable overhead. Guided by the value providers built with VClinic, we can achieve significant speedup for real-world programs on both platforms. VClinic is publicly available at GitHub. This concludes my presentation, and I'm available for questions.